on the homework assignments I've graded so far, a few of you guys were like, oh, I looked at the answer, I copied the answer, but I don't really understand what they did or why they did that. So when we're taking a look at a question like this, one question you want to ask yourself is, have I seen anything where when I take the derivative of that function, I get what I see in the integrand? And so the answer to that should be like, no, well, we haven't taken the derivative of a function and then got an absolute value function as a result. So that hasn't ever happened. So then that tells us we have to look at this a little bit differently. Also, when I see absolute value function, I might think, okay, well, there was a part in the notes that we had covered the other day where we talked about net distance versus total distance. And if this was my velocity curve, if I put absolute value bars around the velocity function and integrated it, I would get something called total distance. I would accumulate total distance. So that might also come to mind, which might help me figure this out. But ultimately, a graph of this is required to just kind of think of it, okay, well, I know integrals are area underneath the curve. So absolute value functions, if I go to graph the absolute value function of 2x minus 5 from 0 to 5, I would know that there's a shift that occurs. You guys can figure out the shifting one of two ways. You can set 2x minus 5 equal to 0 to see where your vertex gets shifted. Let me find, there's someone that chatted something. I just want to make sure it's not a question. Okay, so then, so we get x equals 2.5. So that means that the shifting that occurs here is the graph got shifted 2.5 over 3, 4, 5. Okay, and then it's the absolute value function. I can do things like that. I know it's going to go through there with a, if I factored out the 2, that's another way that I could have figured out there's a stretch of 2. Or if I plugged in 0 to find the y-intercept of this, it's 5. So I know that the other side is going to look the same. Okay, so just getting a rough idea of what the graph looks like. And then from here, if the definition of an integral is the area under between the curve and the x-axis, well, the area of this can be achieved by finding the area of what shape? What shape would give you guys the area of that? Okay, so just find the area of a triangle and double it. To me, I think that that's the easiest way to go about it. But we can also find the equation of this line with the negative slope and integrate it from 0 to 2.5, and then double that as well, because we know that it should be symmetric on this side as well. Okay, so geometrically versus doing this by integration. The other graph that you guys see there, or number 25, x squared minus 9 typically is -9 shifted down and then not drawn to scale. You have a 3 and a -3 as your x-intercepts. So typically the graph, I'm going to erase this graph as soon as I just jot it down for you guys. So you see that all of these, there's a part of the function that falls below, and then there's a part of the function that falls above. And if I stick absolute value functions within that, the graph that I really should be visualizing for this is, let's say 9 is up here. The graph of absolute value of x squared minus 9 should look like this part is fine. They're all positive values, but all the negative y values get flipped and then become positive. So this is what the graph of the absolute value of x squared minus 9 really looks like. So for this one, since I don't have a nice geometric shape, it's not like I can use triangles like I did in the previous problems to find the area underneath the curve. What I can do is we're only specifically looking at the area from 0 to 4. So they want this area. And then let's say this is 4. And then this area. So I see that this part, this area from 0 to 3 is above the x-axis. If I integrated x squared minus 9 from 0 to 4, what's going to happen is this area is negative and this one's positive. Because it's net integral without the absolute value symbols. If I want it to be positive, I can force it to be positive by splitting up my integral and going from 0 to 3. And how do you guys make something positive? If I know that if I integrated this, I get 0 to 3 of regular x squared minus 9, it's going to give me a negative answer. How do I force it to be positive? What could I do besides taking the absolute value? We're trying to like work around the absolute value part. Yes, good. You can multiply the whole thing by -1. So from 0 to 3, I multiply that part by -1. Do I have to, yes or no, multiply the part that goes from 3 to 4 by -1? Do I have to multiply that one by -1? No. Okay, the one from 3 to 4 falls above the x-axis, so we're good with that one being positive already. So what I did was I took x squared minus 9, because I can find the antiderivative of that. I can't find the antiderivative of the absolute value function, and I just kind of trick it. I trick it by saying, I know that if I took the regular integral of x squared minus 9, that it would be negative. So multiplying by a negative would force it to be positive, which is what I want ultimately if I'm integrating the absolute value function. If you ask this question on your homework assignment, does that make sense to you guys? I know it was really the setup that some of you guys had issues with. If you ask this question on the homework you submitted, just did that make sense to you guys? Type yes or no, and then if not, can you guys let me know what part of it didn't make sense? Maybe this class didn't have that. Okay, so some people said made sense. I'm not sure if I remember distinctly some people from second period asking that, so I know there was quite a few from that period. So just to a refresher from where we left off, you guys, Friday we did that. Thursday we did that crazy proof on FTC. Today is all about the application of FTC, which is what you guys ultimately need to be able to do. You don't have to prove it, but you have to be able to apply it. So we did one example. So if you guys can find your notes and go jot underneath that, this is going to be example 2 of FTC. And I'm going to start with something basic again, just as a refresher of what we did before. And just for you guys to remember, this is all about what happens if I take the derivative of an integral. And you want to think of this as what happens if I square something that I took the square root of. They undo each other. Okay, so ultimately that's what we proved. The derivative of an integral, and actually let's keep this just, instead of 2x, let's start basic and let's just do x, of 1 over t to the 5th plus 1. So I purposefully made this. On the first example that we did, we could do it the old way. And the old way involved finding the antiderivative first and then taking the derivative of that. And what we saw was that, well, since this will undo this and you're just left with this anyway, we could just simply take the x and then plug it into here. Okay, so I'm going to highlight the where we're doing the substitution. X goes into here. A couple of things have to occur in order for us to do that. First, we have to be able to make sure that we're really taking the derivative of an integral. Secondly, the constant has to be at the bottom and the variable is on top, which in this case it is. So what we're going to do is our answer using FTC now is just 1 over x to the 5th plus 1. And that's it. And notice that with this problem, and with all AP problems actually, what you'll notice is that you couldn't even do this the old way if you wanted to, because you don't know the antiderivative of 1 over t to the 5th plus 1. They purposefully chose something that you don't know the antiderivative of. So you're forced to use FTC for this one, which is good because it's the shortcut way. Okay, so that's example 2. So as we do these, I'm going to throw these what if scenarios to you guys that you might be asking yourself, like, well, that's great, Mrs. Kim, but what if the top is not just x? So what if it's 2x? And what happens then? Okay, so for this demonstration, I am going to do it the old way because I want you guys to have a reason why it is the way it is. It's not just because I told you. Okay, so old way is you would integrate first, and then you would take the derivative of whatever you integrated. Okay, so integrating 1 over t is ln of the absolute value of t, and then definite integral with -5 2x, and then keep in mind at the end we're going to take the derivative of all of that. Okay, so plug in your 2x, you guys get ln of the absolute value of 2x minus the ln of the absolute value of -5. So we've accomplished the first nesting, I suppose, like if you think of the antiderivative as the first step and then the second step as the derivative, now we're on the derivative part. Okay, you guys answered this question. When I take the derivative of ln of 2x, I get 1 over 2x. Is that your whole entire derivative? Is that it for the derivative? No, what else do you guys have to do to it? Okay, very good. Chain rule, people said. Multiply by 2. So we're going to multiply by 2. And then keep in mind for this one, I'm just going to do an arrow with my highlighter through it. But the derivative of the second part of it, your second term, is just 0 because ln of 5 is just a constant anyway. So that's what we saw was the constant didn't matter. Doesn't matter what number is at the bottom of your lower limit of integration. So long as it's a constant, it's good because you're going to take the derivative of it anyway, and it zeroes out. So my final answer using the old way was 1 over x. The new way is using FTC. Say you guys had I'll just rewrite the problem. You see your problem and you're like, okay, well, I have a constant at the bottom, check. I have the derivative of an integral, check. The top is not just x, but it's a variable. So one way I can do this FTC problem is understand that I would plug in the 2x into the independent variable inside my integrand. So in that case, I'm going to plug 1 over 2x in, or 2x in for t, and then realize that when I was doing it the old way, I integrated, then I had to take the derivative. And this part of it, the upper limit of integration, happened to be on the inside of my antiderivative. So when I applied the derivative, there was a chain rule that was involved. So now going forward for FTC, if you guys have anything but x on top, you also, after you do the plugin, have to multiply by the derivative of the upper limit of integration. So this is derivative of upper limit. Okay, so don't forget that derivative part. And then we end up with the same answer, 1 over x. Okay, so that is like kind of trickery number 1. Trickery number 2 would be, let's say this is example number 4, I believe. Is this 4? Yeah. Example 4, we're going to do this, or actually, let's do one more just to make sure you guys understand the new way of doing this. We're going to do this problem here, where this is the same type of problem that we saw in the previous example. We have a couple things to check. We are taking the derivative of an integral. We do have a constant at the bottom. And then I want to keep in mind that this is going to require some type of chain rule because it's not just x. So applying FTC, old rule, or sorry, new way, is taking the ln of x and plugging it in for t. Okay, so my answer is initially e to the negative ln of x. And then because ln of x is the upper limit of integration, I also want to make sure I multiply by ln of x, chain rule, to get 1 over x. So when I look at e to the negative ln of x, there's a negative 1 in the way that blocks like the e and the ln of x. The negative 1 can also go in as the exponent here. So you guys have e ln of x to the negative 1 times 1 over x. What does e to the ln do? Like what is what happens when you guys have e to the ln? It cancels out the same way square root of x squared does, the same way the derivative of an integral does, e to the ln, because they're all inverses of each other, right? So we really have 1 over x times 1 over x, which is 1 over x squared. Okay, so that's example 4. Okay, on to trickery number 2. Okay, trickery number 2 is, this is all the different scenarios for FTC. What if you guys had x squared at the bottom and 0 on top? Of the inverse tangent of t squared plus 1, notice it's an ugly integrand, something we couldn't possibly do the old way anyway. We can't find the antiderivative of that. We're going to use FTC because the first thing checks out, right? We are taking the derivative of an integral. What's wrong with this one? Why is it tricky? What's the tricky part of this problem? Okay, bottom is not a constant. Upper limit is not an x, is not a expression with x in it. So can you guys tell me, let's see if you guys remember, how do you guys make it so that the 0 is at the bottom and the x squared's on top? What could you do? How do you flip it? Anyone know? How do you guys make the 0? Okay, good. Multiply by negative, take a negative out. And we can move actually the -1 all the way out to the outside of the notation and do that at the tail end. So what we do is taking out the negative or multiplying by a negative is going to allow me to flip my limits of integration, which I just totally did not do. So you want the 0 at the bottom and the x squared on top. Inverse tangent of t squared plus 1. And so now we have everything that checks out. So what we're going to do is take the x squared, plug it into t. So inverse tangent of x squared squared, right? Because we're plugging it into t, which is then squared, plus 1. And then you guys, what would I multiply by? What would I multiply by? So that's just having x squared plugged in. What else do you guys have to multiply by? By 2x, good. That's one of the things. And then what else was there? Take 2x and the -1. So I'm just going to stick -2x in front of there. So these problems are actually, I think they're pretty fun. Once you guys know the shortcut, you just have to like play around with the integral to force it to be what you want. So we have the limits of integration are backwards. We had, what if the upper limit of integration wasn't just an x? And then now the ultimate like kind of trickery with these problems is the last example we have here. And you guys tell me what is wrong with this one now. So we have the derivative of an integral goes from x squared to x cubed of sine of t dt. What's wrong with this one? Okay, there's no constant. And remember, when you guys are looking at any type of graph, if you're looking at any type of graph, technically, if you have a start and an end to it, you can split it at any point. Like I can stop it at here. Let's say this was pi over 2 and say, let's look at the integral from 0 to pi over 2, and then we'll look at it from pi over 2 to 2 pi. Or we can split it at pi. And so long as your upper and lower limit of integration has the same constant, we saw that we could merge it. But now what we're going to have to do is, because both of them are variables, we're going to have to split this. Okay, so what we do is we rewrite the integral as two integrals. Just kind of keep in mind that that's ultimately we're taking the derivative of two integrals. We're going to keep the upper and lower limit of integration in the same spot. So let's say this one's going to have x squared on the bottom. This one's going to have x cubed on the top. So maintain where you have the top, upper, and lower limit of integration. And then after that, it doesn't matter. Like this example that I showed you, if I split the integral at pi over 2, I would go from 0 to pi over 2, then pi over 2 to 2 pi, would give me the same thing as 0 to pi, and then pi onto 2 pi. So this value right here, this constant that I'm going to split it at, it doesn't matter what it is, so long as it's the same value. So it has to be the same value. So in this case, I oftentimes just pick 0 because that's just easiest to pick. But I see some students will do like -2 or random 100. Whatever it is, it doesn't matter as long as it matches. So we're doing the reverse of condensing the integrals and then now separating the two. Okay, so from here, now this one is good to go, right? It has the lower limit of integration at the bottom, and then the upper limit of integration is a variable. So I just have to then take my x cubed and plug it in for my t. Okay, so sine of x cubed. What else do you guys have to multiply by? Is it just 3x? Okay, so I see some people, okay, wrote 3x squared. Good, so 3x squared, the derivative of x cubed is 3x squared. And then what do you guys think you have to multiply this guy by, this integral? So this one's got that second trickery going on, right? The 0 is on top and then the x squared is at the bottom. So for that one, we are going to have to negate it. and then we can plug the x squared in. So sine of x squared, and then multiply by 2x as well. So I'm going to stick that 2x here. So -1 times 2x times sine x squared, and then plus this. And all of this is my solution. Aren't these problems fun, you guys? What do you guys think? Not too difficult, right? This is FTC part 2. Any questions? I know for sure your multiple choice has a few of these. Are you guys doing okay? 10:19. Oh my goodness, how does the time go by so quickly? This is to avoid having to integrate. So the shortcut of integrating and then having to take a derivative. So it's like, you know, understanding square root of x squared is just x. It's undoing their inverse properties of each other. So they're just, it's a shortcut way of doing it. So it's like if you had x to the 4th plus 3 quantity squared and then the square root of that, I don't want to sit there and square everything out and then take the square root again, just to get x to the 4th plus 3 as my answer. It's just like showing that the properties allow me to get to my answer quickly rather than having to do it the old way. So I'm going to have you guys in your packet find for me one of the famous types of FTC problems that we're going to work the rest of the week on. I know I kept telling you guys, like, the free response for chapter 3 is really important because it's not like related rates and optimization where it just ends there. It continues in this chapter now as same idea, but now you guys start off with an integral. Okay, so the graph of the function shown above consists of 2 line segments. Let g be the function given by this integral expression. So g of x is really the integral of 0 to x of f of t dt. So now it's like, okay, wait, what? Instead of like a derivative and its function, now it's giving me g of x is this integral. And that's really hard to interpret. So I know one of the questions is, well, where would we see this? Now I want you guys to take that expression, and I expect all of you guys on the free responses going forward for these types of free responses really common on the AP test, FTC type ones, to now think of it as what we just did. Okay, so if I were to take the derivative of g, I would get g prime of x. If I took the derivative of g, it would mean I'm taking the derivative of an integral. Okay, so g prime of x is really the derivative of that integral. So it should be like, oh, okay, I see now that that's FTC, the derivative of an integral. So I see that the upper limit of integration is an x, the lower is a constant. So I can take the x and plug it into here to get that g prime of x is really the same thing as f of x. And if we don't understand this crucial step right here, that g prime of x is f of x, how I got that, then the whole problem, like, that we might miss the entire question just because we don't have that relationship down. So I always tell students, if you guys see this, you guys should write g prime of x is equal to f of x. And that's the process in which it becomes that. Okay, so then now when I go back to my graph, instead of just thinking of this as the graph of f, I'm also going to think of this as the graph of g prime of x. So this is the derivative graph of f. So think of all of the types of questions, and you guys can see B and C are repeating questions that you guys saw on free responses before. So now I'm going to do A with you guys, g of -1 first. Okay, so this one's just talking about plain old g. So if I go back to g is here. G of -1 would mean I would plug -1 in for x, and x happens to be the upper limit of integration. So 0 to -1 of f of t dt. It's like, okay, well now g of -1 means I'm taking the integral of a graph. What is the integral? The integral is the area. So I go back to my graph and I notice 0 to -1. Well, 1, it's going backwards. It's going from a number, the lower limit of integration is bigger than the lower limit of integration. 0 is bigger than -1. So what I'm going to do is fix that. I'm going to reverse my limit of integration. So it goes from -1 to 0. And that's going in the right direction in terms of left to right when you're reading an integral, lower limit to upper limit. And then now I can interpret it. Well, this part of the graph is above the x-axis, and between the area between the x-axis and the curve happens to be a triangle. So all I'm doing now is taking the area of that triangle, 1/2. The base is 1. Oops, the base is +1, and the height is 3. So my answer is -3/2. That's the area between the curve and the x-axis. Okay, so that's g of -1. So this is -3/2. Now this question here is g prime of -1. So if I want g prime of -1, I'm going to look for g prime in expressions that maybe I had before. Okay, that was g. Oh, g prime is f. Okay, so this is the same thing as asking what is f of -1. I go back, everything goes back to the graph. I go back to my graph. This is the graph of f. So if they're asking me for f of -1, I'm going to go to f of -1, and that's a y value. And the y value happens to be 0. So this is 0. And underneath that, or in parentheses, you guys say that's the y value. F of -1 is 0. That's the y value. Okay, so the next question, g double prime of -1. Well, again, we have the graph of f, which happens to be g prime. Now, if they're asking me for g double prime is the derivative of g prime. So back to the graph. What is the derivative of a graph? The derivative of a graph. What's the derivative of a graph, you guys? Go and type it in. What's the derivative of a graph? It's the slope. Okay, so you guys are going to go to -1. Okay, and then we see that it's a line segment. Well, what's the slope of that line? The slope of the graph. So it's rise 3, run 1. So g double prime is 3. It's the slope of the graph.